All right, welcome back, College Chem. We are going to talk about molarity and solutions. This is kind of the beginning of Unit 4. So we're going to deal a lot in Unit 4 with chemical reactions in solutions. So we have to have a good understanding of molarity, okay? So what I'm going to do, I've got a kind of Google Slides I'm going to click through here, and we're going to talk a little bit about what's going on in solution. So a couple of things to kind of point out is, first of all, a solution is really any homogeneous mixture of two or more substances. Now, when we talk about homogeneous, it means the particles are so well mixed, you can't tell it's a mixture. So back to what we talked about with mixtures before, a solution, which could be something as simple as the air we breathe is a solution. It's a mixture of two or more different gases. You can't tell it's a mixture. Or something in everyday world, your salt water, you're boiling something, you've got salt in it, Kool-Aid, Powerade, lots of things that we come in contact with on an everyday basis, you would say is a solution. A solution really has two parts to it, two components. You have solute and you have solvent. The solute is the substance that's present in the smaller amount. It's typically what we think of what we put into the solvent. The solvent is what does the dissolving. Typically with solutions, we're thinking water usually is our solvent, and we put the solute into the solvent. So for instance, if I wanted to make a salt water solution, solute, that would be my table salt. Solvent, that would be water. So I would pour my table salt into water and stir it up, and voila, it makes a solution, right? Now, concentration is just a way to kind of define or look at how the solute and solvent, or in this case, the solution, compares. So molarity, capital M, or molar concentration, is defined as the number of moles of solute per liter of solution. Not per liter of solvent, but actually in the total liter of solution. So it's a ratio. Molarity is moles per liters of solution, okay? Before I show you this little clip here, I want you to see that molarity, which is moles over liters, can be rearranged depending on what you're looking for. If we were to rearrange it to find liters, we do basically cross multiplication. Molarity times liters equals moles, then divide both sides by molarity. You end up getting liters is equal to moles over molarity, or just the cross multiplication part, molarity times liters equals moles. And that ends up being a very normal part of problems we are going to do in this unit. We're going to have to calculate moles based on the molarity and liters given, okay? Let me go ahead and play this with you, and I want you to watch.
Have you ever noticed that Kool-Aid at summer camp tastes weaker than the Kool-Aid that you might mix at home? Camps have a tendency to water down the drink mix and make a more diluted version than what the mix might call for to stretch their money. Solutions with relatively more solvent and less solute are called dilute, while solutions with more solute and less solvent are concentrated. In this diluted Kool-Aid, there aren't very many particles of Kool-Aid, the solute, relative to water, the solvent. The solute is the chemical that's dissolved, and the solvent is the chemical that does the dissolving. In this case, it would probably taste better if you added more Kool-Aid powder and made a more concentrated solution. To measure concentration, chemists use molarity. Molarity is the number of moles of solute dissolved in a solution, and we use the capital letter M to represent it. You calculate molarity by taking the moles of the solute and dividing by the liters of solution. Instead of writing units as moles per liter, you just write a capital M for molar. Let's try an example. What is the molarity of a solution with 0.70 moles of solute and 250 milliliters of solution? Molarity is moles divided by liters. This problem gives us the 0.7 moles of solute, but the solution is given in milliliters, not liters. So we need to convert milliliters to liters by dividing by 1,000. Then we can use that number in our calculation. Do the math, and you get 2.8 molar. Solutions can have much lower concentrations than this, but you don't often see concentrations higher than about 18 molar. Sometimes, for shorthand, concentration will be written in brackets without the letter M. this is what it looks like. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe and follow me on Twitter at SciencePet.
All right, so back to our presentation here. All right, moving on. Let's go to the next slide. When we make a molarity of solution, again, moles per liters, something else to talk about here is, yes, the particles dissolve, but we also have something called dissociation. Dissociate means to separate, and specifically with ionic compounds. By the way, any ionic compound is considered to be a salt, not just table salt, but a salt is just any ionic compound. When you put that in water, if it's soluble in water, it also will dissociate, means it breaks apart into ions. This is just a quick process, and I'm going to give you another video to watch for this, but if I wanted to make a solution of a particular molarity, first of all, you get a volumetric flask. Then you do some calculations based on the volume that you want and the molarity you want to figure out how many moles of solute you need. And then using molar mass, you actually calculate how many grams you're going to need. You weigh out those grams, put it in a volumetric flask with water, stir it up, mix it up, fill up the water to the line. There's only one line on a volumetric flask, and it's a pretty exact line. And so that way we can get a specific volume that we're interested in. And again, I'll show you, there'll be another video for you to watch on how to make a solution. All right, last kind of part of our little first video here has to do with the dissolving of ionic salt. I really want you to watch and see what happens when you put something like table salt, NaCl, in water, how it breaks up.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
All right, again, that is what we call dissociation. And the idea is that the ions completely separate and break apart from each other and are surrounded by water molecules. And you can kind of see in the picture here, the hydrogens are tending to be attracted to, excuse me, the chloride ions, because water molecules are polar. So the positive end of water, the more positive side is the hydrogen, the more negative side is oxygen. The oxygen tends to surround the sodium ions, and so they pull away from each other, they dissociate. Let me go through just a couple little more example here in terms of calculation, and then we'll kind of be finished with this first video. It says for an aqueous solution of glucose, and you probably recognize glucose from biology, determine the molarity of a 2 liter of solution that contains 50 grams of glucose. So we're going to determine the molarity if we have 50 grams of glucose dissolved into a 2 liter solution. All right, so the first thing we have to do is we have to look at our 50 grams, right? We have to look at our 50 grams of glucose. And we need to change that from grams to moles, right? So we're going to calculate the molar mass of glucose. And so you look at the periodic table and you say, well, hey, that's 6 times 12.01, right? Plus 12 times 1.008 plus 6 times 16. And you add all of that up, and notice I actually have here in the PowerPoint in front of me, it only goes to the tenths on this one. So we'll go 4 sig figs 180.2. And so if I do that, then I can convert my 50 grams, 50 divided by 180.2, that's going to give me 0.277 moles of glucose, C6H12O6, right? And if I know my volume is 2 liters, right, then I can say, take my, if I want to calculate molarity, I'm going to go moles over liters, right? So I can take my 0.277 moles over my 2.00 liters, and that's going to give me 0.139 molarity for my solution, right? So that's the first part of the problem, is calculating my molarity. Now here's the second part, part B. So that was part A. Part B is asking me to, it says, what's the volume of the solution that would contain 0.250 moles of glucose? So let's say I have this solution and I want to pour out 0.25 moles of glucose. What would my volume have to be in order for that to occur? So here's what we do. We go back to, let me do this problem right here. We go back to our molarity equation. Molarity is moles over liters. And if I rearrange this equation, do cross multiplication, what ends up happening is my liters is really equal to moles over molarity when I rearrange my equation. So for part B, if I really want to find the volume, all I have to do is take the moles given, 0.250 moles, divide by my molarity of the solution I'm using, which is 0.139 molar. And so I punch this into a calculator, 0.250 divided by 0.139, and that tells me that my volume is going to be 1.80, because I'm going to round to 3 sig figs. That's part B of my problem here. Okay. Part C is asking for the number of moles of glucose in 0.5 liters of solution. So again, assuming we have the same volume, the same molarity of solution, this 0.139 molar, and I pour out a half a liter, 0.5 liters, how many moles would that be? So again, go back to our molarity equation. Molarity is moles over liters, right? If I cross multiply, molarity times liters equals moles. So therefore, if I take my 0.139 molar and I multiply it by 0.500 liters, then I get 0.139 times 0.5. It actually tells me I get 0.0695 moles is how much I would have, okay? So all this is showing you is you can use molarity equation as moles over liters. You can rearrange it to find the volume, or you could actually find the moles if you know the molarity and liters of solution, right? All right, moving on to, I already went through all this with you. Moving on to the next thing. One thing you will notice when we have concentrations of solutions, the solution that has color to it, maybe it's a copper 2 sulfate solution or a potassium iodide, the darker the color, the higher the concentration, right? And if we were to dilute it, what we mean by that, we mean water it down. We add more solvent and get it less and less concentrated. You're going to see those colors start to fade away. And that's really what the dilution process is. Electrolytes. Let me just mention this briefly. Electrolytes, you hear this term a lot when you think about something like Gatorade. They always advertise, hey, restore your electrolytes after working out by drinking Gatorade. Well, electrolytes are just ions dissolved in solution. That's all they are. So an electrolyte is a material that conducts electricity when dissolved in water. Things like strong acids, strong bases, which we'll get to very soon, and any soluble salt is considered to be a strong electrolyte. And it really is because there's this dissociation breaking apart into ions in water. Things that are weak acids or weak bases, again, we'll get to that soon, they don't dissociate very well. Or things that are just barely soluble, not very soluble in water. We might get a little bit of electrolytes. We call those weak electrolytes. And then covalent compounds that do not break apart into ions at all, those are non-electrolytes. And when we get into acids and bases, we'll kind of show you the the light bulb conductivity tester. When you put it down in, the light bulb lights up if there's a lot of ions present, and it doesn't light up if there isn't, or if it's very weak, okay? Last thing I want to mention here, I know I keep saying it, but here's the last thing. With dissociation, one of the things you're going to have to look at is the difference between the molarity of the compound and maybe the molarity of the ions. Because we're dealing with ions dissociating, we're going to have some conversations, we'll do some calculations with the concentration of ions. So if I look at my picture here and I look at my problem, it says I have 4 moles of NaCl in 2 liters of solution. What's the molarity? Well, that's easy. You take the 4 moles divided by 2 liters, that gives you a molarity of 2. If I do the same thing with another solution of 4 moles of barium chloride in 2 liters of solution, we would come up with the same concentration. But what if we only cared about chloride ions? What if we only cared about specifically the concentration of chloride ions in solution? Here's what we would have to think about, is that NaCl, whoops, let me back up one. NaCl, when you put it in water, it dissociates to sodium ions and chloride ions. For every piece of sodium chloride, I actually get 1 chloride ion. So following the math here, if each NaCl has 1 chloride ions, then I would still be having 4 moles of chloride ions. I would divide that by 2 liters, and we would still say the concentration of chloride ions is 2 molar chloride ion concentration, because this is a 1-to-1 ratio, right? Now, it's a little different with barium chloride, because if you look closely there, barium chloride, if you were to put that into water, each piece of barium chloride breaks apart into a Ba2+ ion and 2 separate chloride ions, right? So think about it, we've got a 2-to-1 ratio going on here. So every time you have 1 piece of barium chloride dissociate, it actually doubles the number of pieces. So if I have 4 moles of barium chloride in my 2 liters of solution, we really end up having 8 moles of chloride in that 2 liters. Therefore, our molarity of chloride ions actually becomes 4 molar. It becomes twice as much, right? And we're going to have some shortcut ways to do this in the next video on how